You might be thinking, okay, that algorithm is cute, but on some maps, maybe it can never find the destination. Here's a complicated maze on the left. Do you think that bug pathing will be able to find the destination? No, really, do you think so? Well, let's look anyway. I'll press the spacebar and run the simulation. At times when it turns around, recall what's happening. It has a follow mode and a free mode. So sometimes, even though it appears as though it's following the maze, it's exiting that follow mode and going into free mode so that it can exit a pathing obstacle and go into free space. However, because this map is itself actually entirely enclosed by obstacles, wow, it worked. Because the map is entirely enclosed, exiting that follow mode and going into free mode can sometimes cause the state machine to end up going back on itself and covering paths it's been before. So then you might ask, looking at this again, in those times when it goes back on itself and is located at the same position as it was at before, what is different about that time? See here, it's headed down this route again. Why does it not stop at the same point as it stopped before? See, it continued on. It didn't stop there. And that's because, did you guess already? Because this is now the location that is closest to the hole, not some previous location like here. Maybe before it was following at this location and then went into free mode because it got closer than it was, and now this is the closest location it's ever been to the hole, and it'll only stop pathing when it gets closer than this. Look at this tile. This tile is closer than this one to the destination, not by a lot, but by a little bit. And the moment it got there, it went back into free mode and tried to go straight to the destination. But of course that didn't work. It hit this wall, and now it's going to follow this wall, and it's going to have to go all the way around a long way again. Okay. So I hope you're convinced, looking at this, that even though bug pathing is not very efficient in terms of the length of the path, it does guarantee that you're going to get there. Let's try refining this path just for fun. I'll press the R key, and almost right away, the extra paths are cut away, and we see that this is the path we need to take. All right, so let's move on. I'll close this, or maybe I'll leave it open. On the right, we have the source code for example6.py. This is like the previous example, where I've made so many files and so many methods that some of them I had to hide away in the closet to clean my room. So we've got two closets here, or extra files that we'll look at later. We've got E6S. I made up a name that sounded like example6 support, and then bug. So E6S is a support file for saving and loading and that kind of thing. And then bug is a pathing file that handles most of the pathing functions. I could have put them all in one file, or I could have 10 files. Organizing things is sort of up to you. Okay, let's see how this program runs. When we look at example6.py, this file here, we're going to be looking at mostly the user interface. That's what I've grouped together. Here's the place where we load the picture of the soldier and that location where he wants to go, which is called a den because of how Battlecode 2016 worked. I specify a pathing start and end location, and I initialize the pathing with p equals pathing, give it a map, a start, and an end. You'll see this pathing constructor for the pathing class in the bug.py file, which we look at later. Then we have one of these while going loops for the game with a 20 frame per second rate. Okay, first I increment the time. This allows us to do something like move the character at a reasonable speed. Next, we look at the keys that have been pressed. We check to see if a key has been pressed. If it's a space, then we pause or unpause the game. If it's a C key, we can make a new map, and that's also hidden away in the support file. We can save the map, again from the support file. We can load. We can reinitialize pathing. We can set step equals true, and we can apply pathing refinement. The user modifies the map simply by passing the user mouse press, which is to say whether he's used the left mouse or the right mouse, since the right mouse erases and the left mouse draws walls. And we tell it the mouse position and some information about the map. If the step value is true, so if step, then we will call pathing.nextStep. We'll ask for this pathing object to execute one more step, and then we'll turn the step off. So that gives us just one frame more of pathing. If we're not paused and time modulo frames per update equals 0, so if you set this to 10, you could get it to run more slowly, then we'll do one more step. Okay, lastly, we have a render method. We have a draw map function in the support file, which will draw the underlying map. Then I have this additional manual drawing function for drawing these blue tiles associated with the path. So for loc in p.path, so here we're directly accessing a list of locations from the pathing object, p.path, and we draw each of those locations in blue. And then we draw on the screen a white rectangle for the player's current point, p.cpt. Then we draw on the map the sprites associated with the path. Those sprites are indicated here in path sprites. So here I've sort of passed in either map colors or path sprites as a command to this draw map function. You see here I use map colors, and here I use path sprites. That command looks at the value. If it's a tuple like this, then it treats it as a color and draws a rectangle there. If it's a string like 0.bmp, then it looks for a sprite that has the same string name. More on that later. Okay, then it flips the display. So that's the whole setup. It's a very simple program, or at least it's made simple, by the use of these support directories. In the next video, we'll look at how the support directories handle those things, and then we'll look at bug pathing in even more detail. See you next time.